Hello, class.
Oh, Hazel. Oh, Hazel. Oh, you sweet.
Hello. You know something funny? When I was younger, instead of wearing hair gel, when my hair was wet, I would take a hat and I would put it on and I would give it a turn, which would take my bangs and push them to the side so that they would permanently stay to the side, and it had the same effect as hair gel. A little tip for you if you want to save money on hair gel. How many viewers do we have? All right, I'm just going to start. All right. So, today's lesson is going to be about two things. First of all, orbits, and second of all, gravitational potential energy. Okay? So let's talk about orbits first. And in particular, we are going to talk about circular orbits. So the general shape of an orbit is not a circle, it's an ellipse. But, the math gets considerably more complicated if you have non-circular orbits. So we're not going to worry about that. All right. And we're going to talk about circular orbits where, if you have two things that have equal mass orbiting each other, then they actually dance around each other like this. If one of the objects is much more massive than the other, then the one that's much more massive basically stays put and the other thing goes around it. It does move a little bit, but not very much. So we're going to consider circular orbits where one of the masses is much, much greater than the other mass. So a good example of that would be a moon orbiting a planet, or a planet orbiting a star, something of that nature. Okay? So whenever that happens, that means one of the objects is going to be pretty much completely fixed. All right? So, So we will have a central body, which would be like a star, of mass big M. Okay, so I will use the margin M, big M. And then we have the satellite, which has a mass little m, okay, which is orbiting at a distance r from the center of the central body, okay, in a circular orbit. Now remember, because of the shell theorem, this r is the distance from the center. Now most of the time that doesn't matter, okay? Center, surface, the difference between those two is a very small difference usually compared to the entire distance. So usually that doesn't introduce such a large error, but technically r is the distance from the center. So now we're going to use Newton's second law. Newton's second law for the satellite. Okay? So we have net force equals ma. The net force is the gravitational force, which is m times g. All right? Now, we can see that the mass of the satellite cancels out. All right? That's an important point. The mass of the satellite cancels out. So all satellites have the same period. About if they're orbiting, if you had another satellite with a mass m2 that is the same distance away from the central body, it's going to orbit in exactly the same way. So as long as the mass of the satellite cancels out, that's important. Now we learned a formula for a gravitational field the last time, which was big G, big M over r squared. Okay. And furthermore, we learned an equation for centripetal acceleration, which was 4 pi squared r over the period squared. So we can cross multiply, and what we get is gm t squared equals 4 pi squared r cubed. All right? So keep in mind that this is the mass of the central body. Okay? This is the satellite's distance from the center of the central body, and this is the period of the orbit. So this is a really cool equation. I'm not going to talk about it too much because we already discussed it quite extensively last year, but we can use this equation in so many different ways. One of the ways we can use it is if we know the period of an orbit and we know the size of the orbit, we can determine the mass of the central body. So this equation is how we know the mass of the sun. Okay? We can't take the sun and set it on a scale. We have to infer the mass. And this is how we know it, by looking at things that are orbiting the sun. Alternatively, if you know the mass of the central body and you know what the period of a satellite's orbit is, you could figure out how far away it is. Okay? Or if you know the radius of the orbit, you could calculate the period. So, for example, this is used by NASA. This equation is used by NASA. Let's say we want to put a satellite in orbit with a given period. So we can use this equation to calculate what does the altitude of that orbit have to be. Okay? So it's a really useful equation. What if we had not used this form of the centripetal acceleration equation? What if instead we used the v squared over r version of it? Because remember, I gave you a number of different equations for centripetal acceleration. There were actually 3 of them. Okay? This is another one. And so what that says is that gm over r square root is the velocity or the speed of a circular orbit. So that's useful. We can see that as the radius of the orbit gets larger, the velocity of the orbit gets smaller. The speed of the orbit gets smaller. Okay? So planets that are further away from the sun are orbiting more slowly than planets that are close to the sun. Similarly, the more massive the star is, the faster the orbits are. Basically, if the orbits aren't faster, then the gravitational force will pull those objects into the star. So the more massive the central body is, the faster you have to go to avoid falling in. All right, so I think I'm just going to leave it at that, because these are just the thing about orbits and sort of celestial mechanics is it's a lot of just using equations. There's not a lot of creativity in the equations. You know what I mean? It's kind of a little bit one-dimensional, which is kind of a bummer. But so I'm not going to do too many examples because it's just plugging in numbers to equations. The next topic I want to discuss is gravitational potential energy. Okay? So that's the second topic. So we learned the equation U equals mgy. This equation is wrong unless you're close to the surface of the Earth. Why is that? It's because this equation is assuming gravity is constant. But we know that the gravitational field is not constant. It gets weaker the farther away from the central body you get. Okay? So what we have to do, if we want to calculate the gravitational potential energy, we have to use the formula, which is the integral of f dr, negative the integral of f dr. So if we go ahead and use the gravitational, force, which is big G times little m times big M over r squared. Okay, and actually it has a minus sign because it's an attractive force, so we got double negatives here. All right. So we do that, we can get the gravitational potential energy. And the result is that the real formula for gravitational potential energy is minus big G times little m times big M over r. So it's not over r squared, it's over r. And it has a minus sign. So this is the real formula for gravitational potential energy. All right. So what does it look like if we were to graph gravitational potential energy versus r? Well, it's actually negative. Okay. So if two things are infinitely far apart, if their r value is infinity, for example, okay, then the gravitational potential energy is 0. All right. And if they're really close together, then you get a big negative number. So what this graph looks like is it looks something like this. So two things are not, so we kind of have a weird, it's a little bit different from what you're used to seeing. So notice how the gravitational potential energy, the old formula, is always positive. Okay, this one is always negative. All right, but the key point is that they both increase as you gain elevation. So this is getting more positive as you increase your elevation. Okay, and the reason it's bendy is because the gravitational force actually changes strength. This equation was derived assuming that the gravitational force is constant, independent of altitude. So from the point of view of celestial mechanics, if two things are not interacting gravitationally, they have a gravitational potential energy of 0. Okay? So something is free. So in other words, it's escaped the gravity if the gravitational potential energy is approximately 0. Okay? It is bound to that object if the gravitational potential energy is less, is the more negative it is. I should say it's more bound the more negative it is. Okay. So let's do some applications of this formula. Okay. One application is to talk about the energy of a circular orbit. Well, the energy of a circular orbit is going to be the kinetic energy of the orbit plus the potential energy. The formula for kinetic energy is 1/2 mv squared. Okay. The gravitational potential energy is negative big G times little m times big M over R. All right. Now, what if we use the equation for the velocity in a circular orbit? So if you're in a circular orbit, the velocity is square root of G times big M over R. So when you square that, you get 1/2 times G times little m times big M over R minus G times little m times big M over R. So 1/2 minus 1 is negative 1/2. So we have negative G little m big M over 2R is the energy of a circular orbit. Okay? So the energy is negative because it's indicating that the planet is bound to the star. So negative energies mean bound. 0 or positive energies mean free to escape and go away. All right? So this is one of the things I like about this equation is the following. Let's suppose you have a star, okay, and you're in a certain circular orbit of radius r1, and you want to move into an orbit with a higher altitude, so maybe r2. All right. So obviously, to make that transfer of orbits, you're going to have to fire your thrusters. Okay. So the question is, how much work do the thrusters have to do in order to raise the orbit into this altitude? Okay. And so basically, what we would do is we would say, well, the original energy plus the work done by the thrusters is equal to the final energy. So the original energy is minus little g, or big G, little m, big M over 2r1, plus the work done equals the final energy, which is minus g, little m, big M over 2r2. So this is really neat because we can calculate how much energy we need to go from one orbit to the other, which in turn allows you to calculate how much fuel you need to bring, etc. So we can start to plan missions with this equation. What do we need if we want if we want to do a mission that can do this, for example? So I think that's really neat. All right. So another thing we can talk about is something called escape velocity. All right. So what is the escape velocity? Well, if you were to throw something straight up into the air, gravity is not constant. Gravity gets weaker as the thing ascends. So what if you could throw something so fast that it leaves the gravitational influence of the Earth before Earth's gravity can bring it to a stop? Then it's going to go up and it's never going to come back down. Okay? That's called the escape velocity. So the speed at which you go up but don't come back down. I should say it's the minimum speed for which that can happen. The minimum speed for which you go up and you don't come back down, neglecting the influence of the atmosphere. Because of the atmosphere, you would have to, go much faster than this speed, but yeah. Now, obviously, this is going to depend on where you start. If you're already in orbit, you don't have to go as fast because you're further away from the Earth. So Earth's gravity is starting out weaker. Okay? So it depends on your starting point. So let's imagine that you are on the surface of the Earth. Okay? The Earth has a radius big R. And we put a rocket on the surface of the Earth. And it launches such that it has a speed v sub ESC for escape. It's the escape velocity. Okay? And it goes all the way over here and it escapes. It never comes back. Okay? It gets really far away. So what we want to do is we want to figure out, we're going to use conservation of energy. So the energy right here is got to be equal to the energy over here. Okay? So the energy right here, we have the gravitational potential energy. All right, little m is the mass of the rocket, and big M is the mass of the planet. And then we also have the kinetic energy, which is 1/2 times little m, because it's the rocket that's moving, times the escape velocity squared. Okay. All right. Now, when it's out here, it has traveled really, really far away from the planet. It has escaped the planet. So that means that R is basically infinity. So if we take gravitational potential energy and we divide by infinity, we get 0. And if it's the minimum speed at which you go up and you don't come back down, when you escape to infinity, the velocity is basically 0 because you barely made it out to infinity, if that makes sense. Okay? If you have more than the minimum speed, then when you escape all the way out to infinity, you still have velocity left over. But this is the minimum possible speed. So your kinetic energy is also 0. All right? So your energy, if you just barely make it out to infinity, is 0. Now, initial energy has to be equal to the final energy because energy is conserved. So we have minus g little m big M over R plus 1/2 mv escape squared equals 0. All right? And so we can take this and we can solve for the escape speed. And if you do that, you work out the math. Notice how little m cancels. And what you get is square root of 2 big G big M over R. Okay? So that is the escape speed. An interesting point is that the velocity of a circular orbit is square root of gm over r. The escape speed is square root of 2gm over r. Okay? So the escape speed is square root of 2 times the velocity of a circular orbit. All right? Now, square root of 2 is 1.41 or whatever. So basically that means if you're in a circular orbit and you increase your speed by 41%, then you'll leave and never come back. All right? So that's kind of an interesting point. So yeah, if you're in a circular orbit and you want to go away and never return, you increase your speed by 41% and you'll leave. I like that. Let's go ahead and do an example here. Let's calculate what is the escape velocity for Earth. Okay? Earth, and I should say from the surface of the Earth. So if you want to get a rocket into space and have it never come back to the Earth, never fall back down, this is the speed you would have to get. Well, the mass of the Earth is 6 times 10 to the 24th kilograms. The radius of the Earth, so we're assuming this is from the surface of the Earth, 6 times 10 to the 6th meters. So we get that the escape velocity is square root of 2 times 6.7 times 10 to the minus 11 times 6 times 10 to the 24th divided by 6 times 10 to the 6th, square root of all that. And we get about 11.5 kilometers per second. Okay? Which works out to roughly 8 miles per second. Or maybe it's 7 miles, like 7. Yeah. Roughly 7 miles per second. So that's crazy fast. So if you were able to throw a rocket or throw a baseball upward, neglecting air resistance at 7 miles per second, so 28 laps around the track per second, it would go up and it would never come back down. All right? So this is basically any interplanetary mission that NASA, they have to at least achieve a speed of 7 miles per second. So just think about how fast that is. That's crazy, crazy, crazy fast. Okay? Crazy fast. All right. Let's talk about, next thing I want to talk about is what if the escape velocity was equal to the speed of light? Okay? What if the escape velocity was equal to the speed of light? In that case, we would have c equals, all right, c equals square root of 2g times big M over R. Okay. And we can square both sides. So we get c squared equals 2g big M over R. All right. And then we can rearrange this, and we get, if the escape velocity is the speed of light, we get that the radius is 2g big M over c squared. Okay? So this is called the Schwarzschild Radius. Okay? And basically, if you had this much mass contained within a sphere of that radius, the escape speed would be the speed of light. In other words, since nothing can go faster than the speed of light, nothing could escape. Okay? So what you would have is a black hole. So this equation sort of hints at the existence of black holes. Okay? So this is the radius of the black hole. Okay? That's the radius of the black hole. So, yeah. We could calculate, let's just go ahead and calculate it for Earth. Okay. So for Earth, and by the way, the speed of light is 3 times 10 to the 8th meters per second. So the Schwarzschild radius of the Earth is going to be 2 times 6.7 times 10 to the minus 11 times 6 times 10 to the 24th divided by speed of light squared. And we get a radius of approximately 1 centimeter. Okay? So this is kind of crazy. So basically, if we took the Earth, the entire Earth, and we compressed it within a sphere of radius 1 centimeter, only once we've compressed it by that much, it would turn into a black hole. So that's an incredible amount of compression. We're taking the entire Earth and we're compressing it by a factor of millions into this tiny sphere of radius, diameter 2 centimeters, so it's only about this big. So if the Earth were a black hole, it would be tiny. It would be only about this big. Okay? So I just think that's funny. So how do you achieve that amount of compression? How do you compress it that much so that it actually turns into a black hole? Basically, you need a supernova explosion. Okay? Because what happens when a star dies is there's a supernova explosion, so the outer atmosphere of the star gets blasted away. But according to Newton's third law, if you have a giant force on the atmosphere of the star sending it outwards, you have a giant inward force on the core of the star. And so it's basically the core of the star that gets the inward force, which compresses it down within its Schwarzschild radius, and it becomes a black hole. Okay? So, yeah. Now, here's another really, really, really crazy idea that that I read about. So there is thought to be a 9th planet in our solar system. Okay, a couple years ago, maybe 5 or 7 years ago, a pretty convincing scientific paper came out, and they were looking at the orbits of asteroids in the outer solar system. okay? And the orbits of these satellites was really weird, okay? And it was weird in such a way that it seemed like there could be a planet in the outer solar system that is interacting with those asteroids and flinging them into these weird orbits, okay? So, and it was a pretty convincing argument. I read the paper myself. It's just saying that the likelihood that this is by chance is not very good. And so it said that in all likelihood, there is a planet that has a mass of about 10 Earth masses out there. So it's actually a fairly large planet. It's about roughly a little bit smaller than Neptune, something out there. Okay? And furthermore, they were able to say it's probably in this portion of the sky. If we look at it, if we look for it, we might be able to find it. So since that paper came out, astronomers have been looking for this 9th planet, and they just haven't been able to find it. Okay? And so some people think it's just not there. Some people think we just need to keep looking and we'll find it. Other people think no matter how no matter how hard we look, we're never going to find it because it's actually a tiny black hole, which is crazy to think about. Okay, it's a tiny black hole that has 10 Earth masses. So, could you imagine if we had a 9th planet that was really a tiny black hole, okay, of 10 Earth masses? So that would mean that what would its Schwarzschild radius be? It couldn't be dark matter. Dark matter is too diffuse. Dark matter is never concentrated. It's always spread out. So imagine if there was a black hole with 10 times the Earth mass. That means it would have, see how the Schwarzschild radius is proportional to the mass. So if we have 10 times the mass of the Earth, then it's going to have 10 times the Schwarzschild radius. So imagine if there was a mini black hole that is literally 20 centimeters in diameter. So it's literally this big. Okay? And that's what the 9th planet is. Wouldn't that be just absolutely insane? It would be absolutely insane and exciting. So then they're talking about, well, how would we detect a black hole like this? And the idea that was proposed was because we're never going to be able to see it optically with a telescope. Okay, so they were like, all right, here's what we do. We send out mini spaceships in every single direction. Okay, so the idea would be to use, like lasers to. So we put all these little miniature spaceships, like a gram, really, really light miniature spaceships, and we send them out in every direction on an escape trajectory. So it's going to escape the solar system. All right? So all these things. And here's the hard part technologically. You need an incredibly light spaceship that has a timer on it, a clock. Okay? And furthermore, that clock needs to send its signal back to Earth. Okay? So if you could send these spaceships in every direction, if you sent enough of them, you're never going to get a direct hit because it's only this big and it's so far away from the sun. But maybe you could get relatively close to the black hole. Okay? And if you've seen the movie Interstellar, you know that strong gravitational fields slow down time. So what would happen is, we're getting regular signals from all of these satellites, and then some of them go close to the black hole, and their signals get slowed down. So then we can say, the black hole is in that part of the sky, so we can then isolate where it is and investigate further. So that's a crazy idea. Which would be Like, think about how that would change our view of the, because astrophysicists are kind of not sure. We know that um, we know that black holes are extremely common in the very center of the galaxy. We know that they're left over from. So basically, every galaxy has a supermassive black hole at its center, with a mass of like millions or even billions of solar masses. So incredibly heavy black hole in the center of our galaxy and of pretty much every galaxy we've seen. But and then also we know that black holes can be formed when there's a supernova explosion. But a supernova explosion leaves a black hole that has a mass of several solar masses. So the question is, if it were a black hole, how do you get a small black hole? All right, it would be a complete mystery. It would completely transform. It would be a crazy discovery. Okay, so got some really good questions in the chat. One is, would the outer planets start to get drawn to the black hole? No, and the reason is that a gravitational field from a black hole, like what if the sun transformed into a black hole? Nothing would change because we're the same distance from the sun and the sun's mass didn't change. So all that determines the gravitational force is mass and distance. Okay? What's special about a black hole is that the mass is concentrated into such a small space. Okay? As we learned in the last lesson, the strongest gravitational field is at the surface of a body. Okay? So if you have something that's really big, once we get to the surface, that's the maximum gravitational field approximately. And so the gravity gets weaker as we go inside. So a black hole is so small that the gravitational field increases dramatically as we get close to it. Okay? That's what's special about a black hole, is the concentration. But if something were to turn into a black hole, our orbit wouldn't change. All right? Because it's not exerting any different of a gravitational force on it. But if something were to come close to it, the gravitation can be much stronger because it doesn't have that surface. And then the question is, couldn't it be detected if light is being drawn in from something that we can't see? So a black hole would be distorting the light behind it. But the thing is, it's just so small that we don't have a good enough resolution to detect the distortions. Okay? We can detect distortions due to the gravity of, like, for example, entire galaxies. But not from a tiny black hole. We don't have the resolution to do that, to see the distortions. Okay, I'm going to move on because I have one more thing that I need to talk about, which is the total gravitational potential energy of a system. Okay, so here's what we do. If we want to know the total gravitational potential energy of a system, okay, what we have to do is we have to sum over all pairs of masses. And when we sum over the pairs of masses, we sum negative big G mi mj over rij. Okay? So we're using the formula for gravitational potential energy, and we have one term for each pair. Okay? So let's do an example. What if we have a square? All right. This square has a side length L, and it has 4 masses, M1, M2, M3, and M4. So, and we want to know what is the total gravitational potential energy of this system. So what we have to do is we have to sum over pairs, all pairs. Now, how many pairs do you have if you have a square of masses? It turns out that you have 6 pairs. There's this pair, this pair, this pair, this pair. But who can tell me what are the other 2 pairs? Type it into the chat if you know the other 2 pairs. And while I do that, I'm going to write down the total gravitational potential energy. So this would be minus big G M1 M4 over L. That would be this pair. Exactly. So the diagonals. So you have 2 diagonals as well. Okay. So that's this pair. So I took care of that pair. Now let's do this pair. Minus G M1 M2 over L. I got that pair. Now I'll do this pair. Minus G M2 M3 over L. Got that pair. Now let's get this pair. Minus G M3 M4 over L. Got that pair. Now let's get this diagonal. Minus G M1 M3. Now the diagonal, that distance is square root of 2L. That comes from the Pythagorean theorem. Okay. So that's divided by square root of 2L. That's that pair. And then lastly, I got to get this pair. Minus G M2 M4 over square root of 2L. So whatever those numbers end up being, that's the total gravitational potential energy of that system. So notice that every term is negative. So, all right. So there's a thing called the gravitational binding energy. Which is equal to minus the gravitational potential energy. So because the gravitational potential energy is negative, the binding energy is a positive number. And it is basically equal to the amount of energy you would need to take these 4 masses and completely separate them apart. Get them so far apart that they don't come back together again. All right? So if we applied this to the solar system, it would be the energy to completely separate the solar system. So that is a useful thing. All right, so that's my lesson for today. And I'll see you in the